1/2, okay, 1/2, sorry, so I need to also multiply this by height, okay, the height of the water, and this multiplied by width. So this would be the net volume. So if I simplify this a bit, this is going to be A plus B plus 24, okay, times height. By the way, we know the width. So the width is really 30. It is fixed for all parts. So the width is fixed for all parts. So this width is really what you call 30. So this will become what you call 50 now. This will become 50. So now we have the relationship between volume and the height. And once you know the relationship between volume and the height, what it remains? Then let's calculate, for example, the derivatives of the both sides actually. Okay, so let's calculate the derivatives of both sides. So once you're going to calculate the derivatives of both sides, for example, okay, for example, what you're going to get? We're going to get something interesting. Okay, so you're going to have dV by dt times 15 of A plus B plus 24 times dH by dt. Okay, so now dH by dt, okay, dH by dt is going to be okay. So before moving to this, actually, let's do first one thing, because there can be one problem actually. The volume now depends on 3 variables, A, B and H actually, while in order to compute the rates you should have one variable on the other side. So the next interesting question could be that can we express A and B in the terms of H? Then we will calculate the derivative, and then we'll calculate the then we'll calculate the derivative, and that will give the relationship between the volumes of the rate of the volumes and the rate of the heights actually. A and B are not fixed. They are changing actually. As the water level will rise, so A is smaller here, A will get bigger, and eventually it can get up to what you call level 6. Okay? So how can we really find this A and the relationship between A and B and H actually? So now you can see that now it is a time to think about 2 triangles. So you have this triangle, okay, this triangle, and this triangle. Okay, so I just redrawn this triangle where this height is, this base is 6 and this is A, okay, and I know about this part that this is H, this is H, this part, and that this total distance is really what you call the 6 feet, okay. So this total distance is 6 feet, okay. So now, if so how can I now, let's use the similarity of the triangle. So if I take, for example, the base of the big right angle triangle and divide it by the perpendicular of the big right angle triangle, this should be equal to the base of small right angle triangle divided by the, perpendicular of the smaller right angle triangle actually. So the base of the big right angle triangle is 6 divided by the perpendicular of the big right angle triangle has the value 6 feet. This is equal to, since both of these triangles, so this small triangle and the big triangles are similar. So this is going to be A divided by H. A divided by H. So therefore we get an interesting result that A is exactly equal to H actually. Okay, so the A is exactly equal to the H. So now I expressed A in the terms of H. So in other words, I got rid of the A and expressed it in the terms of H. Now let's think about the same about this actually, right angle triangle, okay? So let me redraw it. So it goes like this, something like this, okay? Where this is B and this height is small, while this total height is again 6 feet, while this total base is really 16 feet actually. 16 feet. So I can play the same game. Okay, take the base of this triangle, divide by the perpendicular of it. So 16 by 6 should be equal to the base divided by height actually, the B divided by H. So this means B can also be expressed in the terms of the height, and this will become what? So if I simplify this a little bit more, so if I divide this by 2, so this is going to be 3, and this is going to be 8, and this is going to be H actually. So the B is also 8 upon 3, what do you call H? Okay, it's going to be 8 upon 3H. And now we are almost done. So now let's substitute the values of V into the formula. So the V will become 15 times A, which is H, plus 8 upon 3H, okay, plus 24 times H, plus 24 times H, okay. We can simplify this guy a bit more. Okay, I can simplify this, so it's going to be 3 times 1 plus 8, so it's going to be 11 upon 8H, 15 times 11 upon 8H. So let's multiply this as well. So this is going to be 11 upon 8H square plus 24H actually. Okay, so 24H. Okay, and now let's compute the value of the derivative. Let's derivate both sides. So let's derivate both sides. So when you're going to differentiate the both sides, this will become V is 15 times 11 upon 8H. So this is going to be 2H times dH upon dt plus 24 times dH upon dt. So this is what it is going to be, and this is going to be dV upon dt. Okay, so you're going to get this, and once you have this, you have almost solved the problem actually. You have almost solved the problem. Why? Because now you can express the dH by dt in the terms of dV by dt. Okay? So if I pull this dH by dT out of dt out of this bracket, so this dH by dt will become dV by dt divided by, and throw everything else on other side. Okay, so you're going to get this is going to be 11 upon 4H plus, okay, 11 upon 4H plus 24. Plus 24. So this is what is really the major thing now we have got. Now we know about, that dV by dt, the rate at which the, point 8 is changing. Okay. The rate at which, by the way, is the width 30 feet or sorry, okay, so I made a major mistake that this is not 30 feet but it's 20 feet actually. So if this would be 20 feet, so this will be 10 feet. Okay, so if this is 10 feet, this is going to be also 10 feet, 10 feet, 10 feet, and therefore you should also have a 10 here. Okay, 10 here. So now I hope that we are okay. So the dV by dt is really what do you call the 0.8 cubic feet per second, and H in the beginning. I mean, if you read the problem, it says that how fast the water level is rising when it is 5 feet, at the deepest point. In other words, initially at the moment, when you started your observation, okay, it is known that it is 5 feet high at the deepest point actually. So H in the beginning is really 5. And now if I substitute all these values, so you're going to get dH by dt equal to, okay, so the dH by dt would be equal to, after substituting the all values, okay, so substitute all values and get this result actually. So I hope that you're going to get this result, 1.32 into 10 raised power minus 3 feet per minute actually. Okay, so this is what is really the rate at which the height of the water is increasing. So we know the volume of the water, and now we have to kind of think about so we computed the height of the water actually. So I hope this is making a little bit of sense to you, and the problem is clear. Okay, there might be some miscalculation, but I hope that we have done it correctly. So you got the central idea actually. So I hope this solution works for you. So now let's move on to what do you call the next part actually. Okay, let's move on to the next part. The next part. Okay, let's move to the next part. The next question is a very interesting problem where I'm going to use the facts 3 and 4 actually. So in the first problem I used first and second problem. In the next problem I'm going to use the first and the third and the fourth factor. Okay, I'm going to use the third and the fourth factor. So what is the problem? The problem goes like this. Imagine there is a sprinter who is running on a circular path actually. Okay, so we have a sprinter, so an athlete who is running on circular track actually. So he's running on a circular track. So it is given that the radius of the circular track is 100 meters actually. Okay, 100 meters. And there is a person who is located at, for example, this point. Okay, so sprinter is running around this track, and there is a friend of this sprinter who is, for example, who is at the 200 meter distance from the center of the track, actually. Okay, so there is a friend of the sprinter, okay, who is waiting or who is looking at him at this location actually, and this location is what do you call 200 meter away from the center of, so this total distance is 200 meter away. So if this is 100, so this must be 100 as well. In other words, his friend, the sprinter, the friend of the sprinter is 200 meter away from, what do you call, the center of the circle, so it must be 100 meter away from the boundary of the circle, I mean from its nearest point actually. Okay. Now imagine that sprinter is currently at some location actually. Okay, so imagine that he is currently at some location, okay? Currently at a location, or he may be started running, okay, from a location, okay, that is somewhere here, and then he keeps on running actually, okay? So the sprinter is maybe, you know, here at this point, and he is running along the circle. Okay, so he's running along the circle, tangentially along the circle actually. And the speed of the sprinter is really 7 meters per second. Okay, so it is given that the speed of the sprinter when he's running around the circle is 7 meters per second. Obviously, what would be this distance? This distance is also going to be 100. Okay, and it is, so what is this distance? Okay, so it is known actually that when, for example, this sprinter is started running from what do you call a location on the circle, this location initially was 200 meters away from his friend's location. Okay, so initially this location is really what do you call 200 meters away from, so I can say that it's 200 meters away from what do you call his friend actually. So sprinter is running on the circular track, his friend is 200 meters away from the center of the track, okay, and his initial distance, so when this sprinter started running, the distance between him and a point, you know, his friend is, for example, 200 meters as well actually, okay, so this is 200 meters as well. Now what is the key question? The key question is that if the sprinter keeps on running, what do you call, on this track, how the distance between the sprinter and his friend will change over the time actually, okay? How the distance between the sprinter and his friend will change over the time. Obviously, currently, you know, for example, it is 200 meters. But when he gonna come here, it's gonna be more. When he gonna come here, it's gonna be even more actually. So it's gonna be maybe 300 meters. When he gonna come here, it's gonna be even more, and so on and so forth. Okay, and so on and so forth actually. So this is what is really the situation, and in this we have to kind of talk about, for example, we have to think about that how this distance is changing actually. By the way, it is also known, so this is the angle theta, okay, this is the angle theta. So as this guy will, you know, this sprinter will keep on running on the, what do you call, track, this angle will change actually, okay. And say, imagine that, okay, so this angle is really, what do you call, theta actually. Okay, so what we have to do, we have to say that how this distance is changing. So I would like to make this triangle once again, okay. I would like to make this triangle once again, and say this is the triangle actually, okay. While for this I know it's 100 meters, okay, or maybe let's call this A, but we know the A that it's 100 meters always. So no matter where the sprinter is going to be, this side is always going to be 100 actually, okay, because this distance is never going to change. And the distance between the center of what do you call, the circle and the friend is also not changing actually. So this is, let's call this as B, okay, but we know that B is also fixed, so it's 200 meters actually. While this is the distance C, so here is his sprint, here is the sprinter, and at this location you have the friend actually. Okay, so here is the sprinter, and at this location you have friend, and say let's call this angle theta. Let's call this angle theta, and this C is changing over the time. This C is changing over the time actually. Now you have something very interesting, and that interesting thing is A is constant, B is constant, C is changing obviously, and when this printer is running around what do you call this circle, this there is another angle that theta is changing as well actually. So this theta is also changing. Okay, this theta is also changing. So how we going to approach to this problem? So on this problem we can apply what we call the law of cosines. So if this is angle theta and this is the opposite side of the angle, and if I call this C, then by law of cosines I know that C square is really A square plus B square minus 2AB and the cosine of theta, and really the cosine of theta. So this is what is the first relation that we have actually. And if I say compute the derivative on the both sides with respect to time t, so this is going to be 2c times dc by dt. A is fixed, as I am saying, A is 100 always, and B is also fixed, it's 200 always actually. So if I wish, you can substitute these values. So the dc by, and so what would be the derivative of A square? So since A is constant, so this would be 0 plus 0 minus 2 times of, let's put the value of A which is 100, and let's put the value of B which is 200 actually, times the derivative of the cosine theta. Now what is the derivative of the cosine theta? So the derivative of the cosine theta is really what do you call minus sine theta, okay, this is important, times the derivative of the theta as it is changing over the time actually, as it is changing over the time. So if I simplify this bit, so these 2 and 2 will be cancelled, and you're going to get C times of dc by dt is really what do you call this 100 times 200, so the 2 with the 4 zeros, okay, sine theta and d theta by dt. So this is what the relationship between them is actually. So in other words, if you wish, you can divide this by what do you call C. You can also divide this by C, and you can say that initially it is given to you, okay, initially it is given to you that the C, when the sprinter started running, or at some point the distance between the sprinter and his friend is equal to what you call 200 meters. So at one point we will substitute C equal to 200 meters actually. Okay, so initially it was 200 meters. I mean, if you wish, you can really substitute it. So you're gonna get this 20,000 sine theta d theta by dt divided by 200. Okay, so this is going to get rid of 2 and 2 zeros from here actually. So you're gonna get 100 actually. Okay. So the final relation that I'm going to get is really this, that dc by dt is equal to 100 times sine theta and d theta by dt. Okay? So I would like to find this. So obviously now you have two things which should be known to you now. So the first thing that must be known to you, that how theta is changing over the time, okay, and at the point when C is 200, what would be the value of theta? By the way, you can easily calculate this actually. You can easily calculate this. Okay, you can easily calculate this. Or maybe I must calculate it actually. So let's say in this manner. So let's go in this manner. Forget about this one. Okay, so we reached to this conclusion, so this relationship, so we need to calculate now these values. So we need sine theta, we need C, and we need d theta by dt. By the way, can I find the theta and C? The answer is yes actually. First you can find theta and C, and how you can find it, the way to find it is that initially it is known initially it is known, or at some point it is known, that the distance between the friend and the sprinter is 200 meters. So at one point it was 200 meters actually. Okay. So using this formula now, I can also calculate the value of the theta. How can I calculate it? So in this formula, if I substitute value 200 square, and I know the A is 100 square, and I know the B is 200 square, okay, and we also know that it is 2AB, where the 2 is again, so in other words, in this equation, if I substitute C equal to 200, I can get the value of theta actually. I can get the value of theta. So this is going to be 2 times of 100 times 200. Okay. So I want to sort out all quantities, and in the end then I'll calculate the d theta by dt times cosine of theta times cosine of theta actually. So if we simplify this, and I'm leaving this simplification to you, you can actually check that the cosine theta, okay, so the cosine theta is really, by the way, this must be plus, I think, yes, because a square plus b square, so it's not negative. So you can get rid of these two terms. So that means that the cosine theta, so if you take the cosine theta on the other side, is going to be 100,000, so 10,000 divided by 2 times 1 times 2, so it's going to be 4 and 4 zeros, 40,000. Okay? 40,000. So I hope I'm not making any mistake actually. So if we have this, it's going to be 4 zeros. Yes, it's going to be 4 zeros. So the 4 zeros will be cancelled with the 4 zeros, then you're going to get 1 4 actually. So this is cosine theta. So when C is 200, initially is 200, the cosine theta is 1/4. So the theta can be calculated as cosine inverse of 1/4. So you can, pull out your what do you call calculators and calculate theta, or you can do another thing. So if we know the value of cosine theta, then we can also calculate the value of sine theta without even calculating the value of theta. Why? Because I know that sine square theta plus cosine square theta is 1. So the sine square theta is going to be the square root of 1 minus cosine square theta, which is going to be 1 minus 1/4 square. So the sine theta, after pretty much simplification, you're going to get to a square root of 15 by, so 16 minus 1 divided by 4, so a square root of 15 by 2. So when C is 200, the sine theta is 15 by 4. So we can substitute these two values here. So let's substitute, say, dc by dt, and this you have this 20,000, okay, 20,000 times sine theta, which is the square root of 15 by 2, okay, divided by 200, okay, 200. So this 2 and this will cancel out, and this will become, 20 will be gone with 20, okay, and this, so you're going to remain with the 100, and this is going to be then become 50, and dc by d theta. So really, no, d theta by dt. So really the final thing that you got is dc by dt equal to 50 square root of 15 and d theta by dt. Okay, this is what the final result we got. Now, what we have to do, we have to try to find that how the angle is changing over the time actually. And this would be the point where we're going to use this relationship. Okay? This is going to be the point where we're going to use this relationship. So let me get rid of the first part and see that what do you get actually. Okay? What do you get? Now,